Have you observed from there? How are the skies?
I have never been there. I have been there when I.
From last time. Remember last session we covered what are deep sky objects. I gave a general intro to why I do visual observing and what is visual observing. And we went over what are deep sky objects, and we went through various types of deep sky objects. And then we went very deep into the human eyes physiology, and we said how this translates into practical uh, aspects of doing visual observing, especially averted vision, using red light in the field, and also how dark adaptation is precious and we should do everything possible to preserve it. I was very entertained by the discussion we had after the talk. I learned a lot from it. So thank you for giving me the opportunity to, bring up these topics and learn more about them. So today we will start with visibility of deep sky objects. I won't go into the theory, although I prepared slides on the theory. I think it is, I don't have enough time, and I think it's, not very practically useful. So I'll skip the theory, and we'll talk about what are the practical aspects of assessing visibility of deep sky objects. We'll talk about planning and observing session, and this talk is going to be mostly very practical and deep sky observing. Hopefully, my plan is to get to somewhere around here. If you can see my cursor by end of the hour, the hope is that after this, if you have clear nights, I think some of you should try doing some of the things with try going over some of the things that we have discussed in practice. I would say try to observe from your rooftop whatever you can within the urban light pollution, and see if some of these ideas make sense to you. Okay, so let me get started. So measuring brightness in astronomy, we normally measure the brightness of an object through the magnitude scale, right? And remember, I assume that everyone has familiarity with magnitude scale. Otherwise, here's like the 3-second introduction to it. Magnitude is a number which says where the lesser the magnitude, the brighter it is. For example, -5 magnitude is much brighter than 0 magnitude, which is much brighter than 5th magnitude. So it's inverted, God knows why. And it's a logarithmic scale. That means that a difference of 5 for a magnitude is a change of 100 times. So a magnitude -5 object is 100 times brighter than a magnitude 0 object, which is 100 times brighter than a magnitude 5 object. Okay, and so here's the formula to calculate it over here. Sorry, the details of the formula are not important, except the fact that there's a log and a minus sign. And I here is the total light coming from the object per unit area on Earth. So we call that flux. So it's the total flux from the object. The problem of magnitude, using magnitude for deep sky objects, is that it measures the total light received from the entire object, irrespective of the size of the object. Okay, so for deep sky observers, magnitude is only part of the story. And this is an illustration of why magnitude is not a very good measurement of brightness in deep sky. So you could have two objects that are the same magnitude because they give the same total amount of light. But in one case, on the left, the light is spread out over a larger area. On the right, the light is spread over a smaller area. Okay, so this obviously the same light is spread over a smaller area, so it looks brighter. Whereas this, the same light is spread over a larger area, so it looks fainter. Okay, so the same, even if you have the same magnitudes, you can have objects that are very, very faint and very, very bright. Not very, very, I would say faint and bright. So it's not a very good estimate of how bright something is, although it is still useful. I'm not denying that it's not useful, but I'm not saying it's not useful, but we can do better than magnitude. And the solution is to divide the flux by the area of the object. And then you get something called surface brightness. Okay, so here's the formula for surface brightness. Again, the details of the formula are not so important, other than the fact that there's an area in the denominator, and that area is usually measured in square arc seconds or square arc minutes. Throughout this talk, I'm going to only stick to square arc seconds whenever I measure surface brightness. But that's important because different people use different measurements. Now, so this is basically magnitude, but instead of having this I divided by I ref, we are also dividing by area. So what is the effect of that? So that's the mathematics, but the effect of this is that surface brightness captures this notion that if the light is spread over a larger area, then the object appears fainter. This notion is captured by surface brightness. So the object on the left will have lower surface brightness, and the object on the right will have higher surface brightness, even though they might have the same magnitude. Okay, because it accounts for the fact that the light is spread over a different area. So a good illustration of why this is important is, for example, there's a galaxy called Sculptor Dwarf, which I think has a magnitude of 9 or something like that, but it is impossible to see. Like, it's extremely faint. I haven't managed to see it. I've tried a few times maybe, but I've not managed to see it. Whereas, a regular 9th magnitude object is not at all the trouble. So many 9th magnitude galaxies are very easy. So if you calculate the surface brightness, you will see that one has much higher number. So lower surface brightness means higher number because the magnitude scale has that negative sign. Yeah, the surface brightness captures this. So try to look for surface brightness values. They are better than magnitudes as an approximation. The other subtlety of all of this magnitude and surface brightness system is that should be borne in mind is there is no device that can measure all wavelengths at once. So when you get the light from the celestial object, whatever star or galaxy, it is spread over various wavelengths of light, right? There will be some in the ultraviolet, some in the infrared, there'll be some red color, there'll be some green light, there'll be some blue light, and so on and so forth. The brightness that you can see at night is restricted by that by the response of the eye at night, like that scotopic vision curve that we went in last time. I can go quickly back to find it. So I'm talking about this curve, right? This curve determines the response of eyes to various wavelengths of light at night. And so if you're calculating the magnitude, it should be in that region. That we should be multiplying the spectrum of the object by that curve and integrating it. The problem is magnitudes are defined through standard filters called Johnson. I think they're called Johnson filters or UBVRI filters. These filters are defined by professional astronomers. B stands for blue, U stands for ultraviolet, V stands for visual. The visual filter here apparently captures the daytime response of the eye, not the nighttime response. So the visual magnitudes that we talk about are actually not the visual magnitudes we can see at night. So there's a difference between the two. And so that's what is said here. Visual magnitude emulates photopic vision and not scotopic vision. And unfortunately, there's no standard formula to convert between these magnitudes. I mean, you can make some empirical formulas that will sometimes work, sometimes not work, because some object might have an emission line and that will totally change things. So therefore, you cannot write one formula for all objects. So the moral of the story is that, whatever magnitudes we see in the book, even if we convert them into surface brightnesses, they are not very good estimates of whether you can see an object or not. And even surface brightness is not enough for the following reason, that it assumes that the object is uniformly bright. Now, approximately uniformly bright DSOs, by uniformly bright, I mean the light is spread evenly over the entire surface. This happens in some dwarf galaxies and globular clusters, but most galaxies, have a bright core most nebulae have structure. They have bright regions, they have dark regions. So if you just divide by area, again, you're not going to get a very good estimate of how bright an object is. So what I'm trying to say here is, yes, there are like poor man's measures of how bright or how faint an object is, but they will like magnitude, like surface brightness, but unfortunately they're not perfect. They're so we'll talk about how to work around this problem and get a sense of whether ultimately the question I ask is this feasible in my telescope, right? And we'll try to answer that question. Yeah, like I said, most galaxies are brighter closer to the nucleus, and the different details within the deep sky object require different amount of effort to see. I forgot to say this. So, for example, there's a faint dwarf galaxy called the Fornax dwarf in the constellation of Fornax, obviously. Now, this galaxy is extremely hard to see, but there's a globular cluster in that galaxy called NGC 1049. This is an NGC object, with a big telescope, 16-inch, 18-inch. You can see it in a dark sky. I remember we saw it first from Kursk with the 17.5-inch. So even if you can't see the galaxy, you might be able to see parts of the galaxy, like the nucleus or the various knots in the galaxy and so on and so forth. So that should also be borne in mind. So that's why surface brightness is also not like a very good measurement. Let's ignore that for now. So this is an important slide. Okay, so all of that was some math and some theory, but here are some examples of high surface brightness objects. Okay, you see how the light is concentrated. Now, I have intentionally chosen these sky survey images. These are from digitized sky survey. This is basically people, professional astronomers in the Palomar Observatory in Southern California. They took images of the entire northern sky, and in Australia they had a southern telescope. They took images of the entire southern sky. So there are images of every part of the sky available. This is pretty old, and they were all done on photographic plates, and they have been digitized. They are not calibrated by professional astronomy standards because these are not done with CCDs and other modern things. They are just plates and they have been scanned. But for amateur purposes, these are pretty well calibrated in the sense that if you see the brightness of an object on this plate, chances are it will give you a good estimate of what is the actual brightness of the object. That's what I mean by calibrated, in the sense that the brightness you see here is kind of real. Now, if the reason I prefer this, that I'm showing you these pictures rather than beautiful pictures taken by the Hubble Space Telescope or amateur astronomers, is because pictures taken by Hubble and amateur astronomers are not calibrated. Like they will be processed differently, and when you process an image like this, you might adjust what are called curves, right? So you might increase brightness of parts of the images and decrease brightness of parts of the images. So that kind of thing doesn't happen here, and that's why this is a very good tool for visual observers. This sky survey. So if something appears bright on this sky survey, chances are it is actually bright. And if something appears faint, chances are it's actually faint. So here are high surface brightness objects. Now my next slide has low surface brightness objects. So this is the difference I'm talking about. So you see, these objects might be very bright because actually these plates are all of different sizes. I've chosen the size of the plate depending on the object. I don't know, they might be the same size, but I think some of them are different sizes. But you go back and forth and you see what I'm talking about. In the high surface brightness objects, the light is concentrated in a tiny region of there's a lot of light concentrated, whereas here there's a lot of light spread out. Right? For example, this globular cluster here might actually be as bright as this object in magnitude, but because the light is spread over a smaller area here in the Turtle Planetary Nebula, this you can probably see from the city. I think I have seen it from city in my younger observing days with 8-inch. Whereas this, we struggle to see it from even darker skies. So this is why surface brightness is a good tool, and so now when I say high surface brightness object, this is what I mean. When I say low surface brightness object, this is what I mean. Light is spread out. So these are very hard to see. Low surface brightness objects are very hard to see. And high surface brightness objects, if you have a good telescope, lot of magnification that you can throw, you can even see them from city skies. Some of them, like this ghost of Jupiter, you can see from the city. M32 you can see from the city. M80 you can see from the city. Turtle planetary nebula you can see from the city, so on and so forth. These require very dark skies. Okay, so like I promised, I'm not going to go into the theory of how faint we can see, but I just want to show a few things of it. Like I won't go into detail of the theory, but we'll go over the general ideas that come from this theory. Okay. First thing to note is that objects at the threshold of visibility are not seen continuously. So here's a curve from one of Roger Clark's articles in Sky and Telescope. I must thank my friend Bob Douglas for pulling this out from his collection. So what this curve says is that fainter objects, you don't see them all the time. They come in and out of your vision. So they might pop, we say popping in and out of the vision, or we say maybe we can see 10% of the time, but not all the time, right? Maybe we can see 20% of the time and not all the time. So this tells you that the fainter objects that you go, the lesser time they are visible, and eventually, of course, the object is invisible if it's too faint. But objects at the limit of visibility, you see them for some time and then they vanish. Then you see them again for some time and then they vanish. This is normal experience. So that's why people talk about the probability of detection per some time window. I understand this looks very scientific, but in practice, we just estimate saying, okay, I could see this maybe 10% of the time, hold it in my vision 10% of the time, and so on and so forth. Sometimes the threshold objects are so faint that we see them like 2 or 3 flashes, that's it. That's everyone's experience. This is just the way the human eye works. This is a part and parcel of viewing faint objects. Okay. Why this happens, I really don't know. I don't know the answer to why this happens, but there are various factors. One of the factors, I'll list them later again, but some of the factors are like the way your averted vision scans across the field of view. Sometimes it might just fall on the right places. The way the eye integrates for light for a certain time, right? And also the seeing conditions, the atmospheric turbulence, how steady the atmosphere is also affects these things. So that is aspect number one. Then here's another important thing. The detection of a deep sky object relies on both being able to detect the light from the object and discriminating the contrast between the deep sky object and the sky background. So what matters is kind of the signal to noise ratio, right? Not how strong just the signal is. So if your background is very bright, then it becomes harder to see faint stuff. And if your background is fainter, like the sky background in your telescope is fainter, then it's easier to see faint objects. So one should not think about just the brightness of the DSO, but the brightness of the sky background and the contrast you're able to discriminate. That's why observing low surface brightness objects is very hard, because they are very low contrast. Now, the rest of these slides, I'm talking about the theory, I just want to say that this theory exists and where it exists. So Roger Clark wrote a book called Visual Astronomy of the Deep Sky. And over there, he has a good theoretical analysis based on some research that happened during the World War of how faint people could see. So they brought test subjects in a room and showed them very faint objects, and they built an experiment to see how faint people can see. And Roger Clark has managed to turn that data into something meaningful for astronomy, and he describes it in detail in his book. But But the key crux of this is that bigger and brighter objects are easier to see. Not just the brightness of the object matters, the size of the size of the object as seen by the eye also matters. And the ability of a telescope is basically to make the object brighter and bigger, both magnification and the light bucket size, right? So anyway, there's a lot of theory in there, and I'm going to skip it. I actually have some slides explaining this, and you can look it over when we share the slides at the end of the series. Anyway, what is more important is what are the practical lessons from the theory. The practical lessons are dark skies are important because it helps increase the contrast of a given object. Okay, C is for contrast there. Second thing, it says bigger aperture makes objects brighter, so it's more useful. I guess the crux of this theory is that it explains why aperture helps, because you would say aperture makes, if I have a big telescope, then the object becomes brighter, but the sky background also becomes brighter, right? The thing is that, and this is everyone's experience, if you look through a big telescope, the sky background looks bright inside the telescope. So unless you are at high enough magnification. And so what this theory says is that the eye is not such a simple sensor, right? The way it perceives brightness is much more complicated. So aperture actually helps. The other key thing is magnification helps up to some point beyond which it hurts. And the idea is that as you magnify, initially you make the object bigger and you make the sky background darker, but you also make the object itself, you spread the light. It's the same idea as surface brightness. You spread the light of the object over a larger region. So the object also becomes fainter, the sky background also becomes fainter, but it becomes bigger. So that effect of making the object bigger helps up to some point, after which you are making the object more and more faint, and so that's not helpful. So there's some optimum magnification for an object and a sky condition. And so so the rule from this, the learnings from this theory is try different magnification. And the theory also says low surface brightness. LSB is my short form for low surface brightness. You might see it all over the place. LSB is low surface brightness. LSB objects get harder to see in poorer skies. By that I mean brighter skies like city skies. So these, I guess, are fairly obvious, except maybe this magnification helps aspect, like bigger objects are easier to see. I should also point out, if you read Roger Clark's book, there is some disagreement between amateur astronomers on how to calculate the optimum magnification, because Roger Clark has some theory on how to calculate the optimum magnification. And many people think it's wrong, including myself. So the general ideas and the general concepts are good, but the exact values might be like not exact. So anyway, few more notes on visibility. So if you're at high power, then the sky background in the scope is darker than in the sky. So what are the implications of this for dark adaptation? I think that if you're observing at high enough magnification, your sky background in the telescope will be so much darker that there is an advantage to dark adapting to the sky background in your telescope. By that I mean, even the sky can ruin, even just looking up at the sky can ruin your dark adaptation under those observing conditions. So that's why we normally use a hood, okay, to block out the stray light, including the stray light from the sky, and dark adapt to the field in the telescope. Few more points. These are all random points of what affects observing. The eye is a very we touched on this in the last talk. The eye is a very complex sensor. It can integrate over time, just like a CCD camera that exposes for 6 or 10 seconds. The eye can also expose for longer durations of time, but it's not as effective as CCD. So I read up more about this. Apparently, the exposure time of the eye can be as long as 6 to 10 seconds. So that's how long you should spend at least at the eyepiece. So when you first go to the eyepiece, if you are at high power, which I will recommend, first your eyes will dark adapt to the sky background inside the telescope, and then your eye starts integrating light. So it takes at least a minute or so in my experience to start seeing some of these objects. So that's why time at the eyepiece matters. And comfort of observing, minimizing effort of the brain matters also. We will talk about this in much more detail. Like you have to make sure you have enough water, you're comfortable, you're not sleep deprived, there's enough oxygen. And Mel Bartels, who is famous for his telescope making, but is also an exceptional visual observer, he has a list of observing factors on his website. He says these are the things that matter and how they affect your observing. So that's worth looking at. So what I'm saying here is it's very hard to say what is going to be visible in your telescope and what is not going to be visible. But the few things to keep in mind are things at the limit of visibility are not seen all the time. That's everyone's experience. And all these small factors, like how long you spend at the eyepiece, how much light shielding you create, and so on, all of these matter a lot. And contrast is everything for low surface brightness objects.
Hi, Akarsh. Question.
Yeah.
So in the last slide, you said the eye can integrate over time. So
Yes.
what does that mean? In the sense that what happens if we blink if we are observing, or what happens if we move our eye during observing? Will it still be able to integrate, or do we need to keep our eye open and just stare at some particular position for a long time? How do you observe?
That's a very good question, and I don't know the answer to that, but I imagine that it means that you have to stare at a place for about 6 to 10 seconds. And I think blinking might not hurt so much because it's so momentary, right? And but what they say is that what I read is that this happens at the level of cells, rod cells in the eye. Like when the neurons from the rod cells come out, they're apparently able to aggregate information in some way. So I'm still not clear on whether it happens in the eye, whether it happens in the brain, because that will determine how the eye reacts to various these changes that happen. But that's why tracking does help. That's why most visual observers recommend having tracking for that reason on their telescopes. Even though they're not doing photography, it helps the eye keep focusing on the same object. So
Okay.
short answer is I don't know, but I imagine that it helps to keep the object in the same place for a long time.
But at least in your experience, if we are moving our eyes, because sometimes for let's say averted vision, we keep moving our eye, and also we always blink. So these don't
Correct.
really hurt the way we observe, right?
I mean, we can't help them, right? In some sense.
Yeah,
And
yeah.
that's probably, I suspect that that's what makes that probability that we were talking about, that you can't hold an object all the time. It might be because of these factors, or that the fact that your eye moves around, the fact that you blink, these things might affect that. So how
Okay.
uninterrupted your integration is a very questionable thing. Like, I don't know how uninterrupted it is, but it helps. Like spending a minute at the eyepiece, definitely you will see a lot more. That there is no doubt about. That definitely corroborates with my experience.
Okay. All right. Thanks.
And I think there are two things contributing to that. One is the dark adaptation, and the other is the exposure.
Okay. Okay.
Okay, so empirical observation. Okay, so I obviously skipped the theory, but these things come from experience. At least they come from my experience. So and I think they are generally true. The point number one is for large, low surface brightness objects, you really need sky quality. It matters a lot. Contrast is very important. We'll talk about how to improve contrast of the telescope. Things like baffling, which means light protection, preventing stray reflections within the telescope, eyepiece quality, these things matter a lot for low surface brightness objects. The anecdotal thing that I've heard is that rich field telescopes, by that we mean small F number telescopes which provide a very large field of view, they work very well for low surface brightness objects. The general advice that stems out of this is if you have poor skies, your skies are not optimum, don't bother with low surface brightness objects. They really, every bit of sky quality improvement makes a huge difference for those objects. So there are other things to see. So on city skies, kind of don't even attempt low surface brightness objects. Wait for better sky conditions because they'll get a lot easier. Whereas for small high surface brightness objects, you can put aperture, you can throw aperture and magnification at them, and they will, get better and better. So if you have aperture power, high surface brightness objects, you can knock them pretty well. So if you don't have the right skies, see, with low surface brightness objects, what my general sense is that an 18-inch in a mediocre sky will be challenged by a 6-inch in a really dark sky. So aperture doesn't take you as far as dark skies does. But for these small high surface brightness objects, aperture and magnification really help. And I think you can connect this back to the theory that if you take the time to read through that theory and understand it. But anyway, this is my experience. I haven't checked it. I mean, I've asked a few amateurs to look at my slides, but I haven't had a huge discussion on this. So take it with a pinch of salt. This is what I've already said. In light polluted skies, focus on high surface brightness objects and capitalize on dark skies for low surface brightness objects. What are examples of high surface brightness objects? They are like planetary nebulae. Not all of them. Most of the NGC planetary nebulae tend to be tight and bright. Tight and bright globular clusters. Again, not all globular clusters are high surface brightness. Some are very faint. Seyfert galaxies. Seyfert galaxies are a kind of active galactic nucleus where the galaxy nuclear core is extremely bright, like Messier 77, M77. You can sometimes see these in the city. Whereas these low surface brightness diffuse objects like dwarf galaxies and so on, best to use dark skies for them. Okay, so that was a long section on visibility of deep sky objects. I know some of the concepts I emphasized here are somewhat advanced, so I'll pause now and ask if there are any questions about it before I go on to more practical aspects. Yeah.
Hi, Akash. There was a question as to whether the surface brightness is proportional to the apparent magnitude.
Yes, definitely. Sorry. If I did not say this very clearly, the surface, let's go back to the calculation. Where are we? Yeah. So you see here, I have simplified this formula. It says magnitude plus 2.5 log of area. So the magnitude is already there. M is the apparent magnitude. So yes, if you have a 9th magnitude object with some area, and you have a 10th magnitude object for the same area, then the 9th magnitude object surface brightness will be 1 higher than the 10th magnitude object surface brightness. So for example, if I have an object who has an area of exactly 1 arcsecond square, then this will effectively be 0. So the surface brightness of a 9th magnitude object with that area of 1 arcsecond square is exactly the 9, and the surface brightness of a 10th magnitude object with 1 arcsecond square area is exactly 10. So it does depend on the magnitude, correct?
Okay, but how do you use this formula? In the sense, let's say when you're talking about magnitude scale, I know that, okay, I can see probably up to magnitude 6 stars I can see through naked eye, something like that. So how do you use this surface brightness?
Very good question. Thanks for bringing this up because I somehow have missed this in my slides. The surface brightness of an exceptional sky is 21.8 to 21.9 magnitudes per square arc second. So the surface brightness of so the unit of surface brightness is either magnitudes per square arc second or magnitudes per square arc minute. That's a bit of a loose term. If you do proper unit cancellation, you see it is actually unitless. But let's stick with that. Okay, we call it magnitudes per square arc second whenever the area was measured in arc second square, and we call it magnitudes per square arc minute whenever the area was measured in arc minute squared. Okay, so 21.8 to 21.9 is the darkest sky you can get. We have sometimes seen 22, but that's extremely rare. Now, it turns out that if you, so that should give you a sense, right? Something that's around 21, 22 is going to be very faint. Whereas something that's going to be 20, 21 is or 20 or 19 is very bright. So I don't have a very good feel for these numbers, I'll admit. But you can calculate for most of the common objects what it is and get a sense of this. It turns out that you can see fainter than the sky background because it's a question of sky background versus sky background plus object brightness. So that contrast makes a difference. And the theory actually tells you what level you can discriminate. But I haven't calculated these for faint objects. So I go more by visual things. So I really don't have a feel for surface brightness. Sky surface brightness, yes, 21.8, 21.9 is the golden number.
Okay. So actually, when we talk about the sky brightness also, I think even the excellent skies probably have around 22 or 21.7, something like that,
yeah,
right? So
correct, exactly.
So the faint objects that you're talking about. So when we talk about this number, is it also kind of the surface brightness of the? Can we say that this is the surface brightness of the night sky?
Yes, it is the surface brightness of the night sky, exactly.
Okay. So even if what you're saying is even if the object has a surface brightness of which is less than this.
Let's use the word fainter so that we don't get confused. Yeah, even if the object surface brightness is fainter than the the night sky surface brightness, you can still see it.
Mm-hmm. Okay.
But not much fainter. So use 22 as a rough estimate of what is really faint.
Okay. All right. Thanks. Then I had another question. What was that? Can you go to the last slide that you were showing?
I guess. Wait, let's see. This one? No, I went one more. Yeah. This one.
Yeah. Sorry. Yeah. Oh yeah. Correct. So the question was. In your experience, like with the 18-inch telescope, what is the magnitude? What is the magnification that we should be using, or maybe even with the current telescope that you're using? How do you? What is the magnification that you use, and how do you decide this?
Yeah, that's a good question. Again, there is no rules. There's no one size fits all because it depends on the size of the object. The best answer is try every magnification, but there is a thumb rule. The thumb rule says 10x for every inch of aperture. So on an 8-inch telescope, that will be 80x. On an 18-inch telescope, it will be 180x. So I observe usually at 200x power.
Okay, great. Thank you.
The more sophisticated version of the rule says, this is what Mel Bartels and Nils Olof Karlin say, is that the object, whatever is the object of interest, should subtend an angle of about 1 to 2 degrees in your eye after magnification. This is what they say is a good magnification. So it depends on the object. But the idea is that
when you say 1 to 2 degrees, so okay, so we have all these eyepieces that have 80-degree field of view, 60-degree field of view. So are you talking about those?
No. I'm not talking about that. So magnification, which you calculate as FO over FE, focal length of objective over focal length of eyepiece, has the other definition, which is if the angle as viewed at the eyepiece divided by the angle of the object in the sky. Right? So if I have an object that is 1 degree in the sky, a magnification of 10x will make it 10 degrees in my field of view. So I'm talking about that 10 degrees.
Okay.
I mean, for a more realistic example would be you have an object of size 1 arc minute. If you magnify it 60x, in your eyepiece, it will appear to be 1 degree.
Okay, cool.
And so that's about the right thing for 1 arc minute size. This is what they say. Again, really no solid rule. I'll go into more about this later, but yeah, you should just try all sorts of magnifications.
Okay, thank you.
Okay, shall we move on to the next section?
Yeah, I think yes. There are no more questions.
Okay, so that was. I'm sorry if that was a little heavy, but I felt like it was worth distilling all of that into one section. Now we are going to talk about much more lighter things, but I feel they are also very important. And some of these might sound very obvious that I'm stating them, but sometimes it takes experience to beat this into one's own head. So I'm going to talk about it anyway. First, a note about observing in long stretches. Observing run of many days is better than many short runs. Okay, the reasons are obvious. There is no driving involved. There is no setup and tear down of your equipment involved. So observing one set of 3 days is much better than observing 3 separate nights. So try to observe for longer durations. But at the same time, more than a week might start to become less productive because you're fatigued. And fatigue meaning that you can't work very well all night, right? After 7 nights, it gets hard. The good news is that there's a natural limit in terms of moonlight, so you won't go observing for an entire month or something like that. So 1 week is a very good time. And comfortable sleep in the morning is important if you are observing for multiple nights. And this is not easy, especially because if you're camping, which a lot of us people do on the field, then it gets very hot in the daytime in your tent, and so you have to think about all of that. How am I going to sleep during the day in the outdoors? If you have a cabin or a house or whatever in the remote area, then it's very good, no problem. But the key message here is try to observe in periods of a week. Okay, how do we choose an observing site? I understand this is a very hard question to answer in South India, and like we were talking about it before we started on the talk. But here are some characteristics that make for a good observing site. The first thing is light pollution. You want as little light pollution as possible. And there is this atlas. Let's see if I can open it very briefly. So there is this atlas of night sky brightness. And it's overlaid on Google Maps, so you can actually see this. As you can tell, the white is the worst and the black is the best region. So if you look at South India, it's a pretty bleak situation unless you go close to this hole or you find something in this hole. But this hole, which is like Coorg and Chikmagalur, has its own share of problems, Korchadri and all of that. And that is due. Anyway, that's the next topic. Humidity. You want humidity to be as low as possible. Not only do you want that relative humidity number, RH number, the percentage to be lower, you also want the place to be as cold as possible because in colder air supports less water vapor, right? So cold places with lower relative humidity will do better for visual observing. In terms of elevation, you want it to be at around 8,000, 9,000 feet, ideally. So this already calls for North India, but we can do whatever we can with what we have, right? And not all of these are like ideal. The problem of going higher than 8,000, 9,000 feet is that you need oxygen. I am told that if you're above 9,000 feet, either you have to spend a lot of time acclimatizing or you have to breathe oxygen from a tank so that your brain is fully able to process all the information. The reason elevation, even a little bit of elevation helps a lot is because the atmosphere thins down exponentially. So the amount of dust, the amount of density of the atmosphere itself goes down very fast. So even a small amount of elevation will help. Then you want in your observing site very good airflow. This is what is called atmospheric seeing, right? You want the stars to not twinkle and the air to be as steady as possible. This especially matters when you are looking at very tiny objects, because then they will, if you don't have stable seeing, they will jump all over the place and you won't be able to integrate the light from them. You want to not have smoke, pollution. You want to have less air glow. Air glow is the natural glow of the air, the oxygen especially, I think, in the air, which happens because of, it's basically like aurora borealis, but it happens at lower latitudes in a small amount, and we call it air glow. And you want as little of that as possible. That's why they say the solar minimum is the best time to observe, because the magnetic activity of the sun is very low, so you get darker skies. This might not matter so much at 13 degrees. It starts mattering at where I am now, around 30 to 40 degrees latitude. And you don't want local lights. Now, local lights don't contribute so much to light pollution, but they can ruin your dark adaptation, cause glare, and all these problems, right? A good observing site, like I said, especially for low surface brightness objects, makes all the difference. So here are some examples, which we might not be so lucky, but the people in Germany, in South Germany, this is where they observe. I'm told that they have exceptional seeing in the Alps. This is an excellent site in California. It's hard to get to from where I am, but Alvin Huey, one of the famous visual observers, has done some very good observations from this place. They say it's very dark and it's at around 8,000 feet. So it's very ideal for observing. Now, of course, pictures like this look very nice. Your site can look much less beautiful, but it can also still be an excellent site, right? The middle of nowhere, flat land is still okay. So how do you, next we are now going to talk about another entire big topic, which is how do you choose objects, where do you look for them, and how do you guess whether they're going to be within the range of your telescope or not. So what are the criteria for a good object? One, it should be well placed during the night. So there's no point trying to observe a summer object in the winter and a winter object in the summer, because it will never come up high enough in the sky. So for example, when Ursa Major is high up, even if Cassiopeia is visible, you should not be looking down there, because 6 months later, it will be a much better situation. Now, I understand in South India, again, you might, the answer is, whenever the skies are there, just run and do as much as you can. But this is for others, like to optimize. Second thing is, it should be plausible with the given sky condition and equipment constraints. There's no point picking something very light, low surface brightness if you know that you're only going to have access to bottle 4 or 5 skies. Finally, it should be interesting to you, right? It should have some reason why you want to look at it. So maybe it has interesting feature. Maybe it is just challenging, and that's why you want to see it. Maybe it completes a series, like you've been observing all Messier objects and it completes the Messier catalog. So that's a good reason to observe something. And maybe it has interesting history, who discovered it, or how it was discovered. And maybe it has interesting science, and that's what you want to see it. Maybe it's very unique kind of object. So these are all the various reasons why you might pick a target. So where do you look for targets? For beginners, it's very easy, because if you haven't done these things, these are the things that are already available to you. And that's the number one, the Messier catalog. the Messier catalog, as we said, has 110 objects. They're all very bright. They're all, I won't say they are all very bright. 90% of them are very bright. And you can see all of them in an 8-inch telescope, maybe even a 6-inch telescope. I know people have seen it in binoculars. So that's a very good thing. Once you finish the Messier catalog, there is what is called the Caldwell catalog. This was curated by Patrick Moore for amateurs. I went over this last session also. So you can go through the Caldwell catalog. It has another 109 objects. And if you're done with that also, I like this Cambridge Star Atlas. Actually, Amar Sharma introduced it to me many years ago. And what we did is we went through the lists of objects that were there in the table of that book. And that's a very good short list to have. Usually, most of them are bright. Some of them, occasionally, you might come across something that's extremely hard. You keep trying, you don't get it. And then you realize it was a hard object. But the Cambridge Star Atlas short list is a good place to go. Now, if you've finished all three of this, there's something called Herschel 400, which is a selection of 400 objects in the NGC catalog that was probably discovered by William Herschel. So this is a thing that comes from the US from an astronomy group called the Astronomical League. So they have an observing program, and you can download their books on Herschel 400 Part 1 and Part 2. So this is very popular in the US. I heard about it the first time after I came here. But it's kind of a set of like bright NGC objects that you can look for, 400 of them. Many people go through all 400. I've never bothered to go through all 400. Okay, so those are places to look for targets. So how do you go about picking for targets? Now, let's say you're not a beginner, then and you're no longer interested in doing, let's say, the Herschel 400. You've finished these three things. Then what do you do about finding more things to observe? So you can go about systematically. This US-based astronomy league that I've mentioned has put together lots of observing programs. You can go to their website. They have various pre-made lists for you to go through. Or you can go choose randomly, hunt the internet for objects yourself, and pick the ones that are interesting to you. So I like doing this because then I observe only the objects that are interesting to me, not because somebody put them in a list. But of course, this means more work in trying to find these objects, putting them in lists, and organizing sessions. So where do I look for objects? One, for challenging objects, there are famous challenge lists. The Royal Astronomical Society of Canada has this nice deep sky challenge list. This has, I don't know how many, but it has some very challenging objects. Steve O'Meara has 3 books on objects that are beyond the beaten path. And the Texas Star Party, actually, this is good for beginners also. Texas Star Party has a pair of observing programs every year. I think this is the first year they won't have anything because Texas Star Party is cancelled. But other than that, for the last 20 years, there's a beginner's observing program and there's an advanced observing program. There are 2 lists that they put together. And the advanced lists are really, really good. I think the beginner lists will also be of the same quality. Obviously, you can tell that I would prefer to do the advanced list. But they put in a lot of work into this. They are very good selections of objects. So those are places to look for objects if you don't want to stick to all of these standard programs. This is my favorite website for finding objects. It's called Adventures in Deep Space. If you search Adventures in Deep Space, you will get this website. Some of the best US-based visual astronomers have written a lot of very good material on lots of amazing objects that you hardly see anywhere else. So, for example, here's a list of galaxy chains. And they have observing reports from various apertures, and they tell you a little bit about the object. This is a very good website to look for interesting material to observe. This book, I cannot recommend this book enough. This book is extremely good. But it's actually part of a series. And you might be interested in the other books in the series. I mean, galaxies are my favorite thing, but there's comets and how to observe them, double stars and how to observe them. There's an entire series by Springer on something and how to observe it or them. Okay, so and all of them are affordably priced. They're not like typical US hardbound books. They are affordable even by Indian standards. And this particular book, Galaxies and How to Observe Them, I think most of my talks content can be found in that book. It's just really good. Their observing lists are really good. The one thing I regret doing is I took this to the field to look through those observing lists, and it's fallen apart because of the dew. So I recommend that you learn from my mistake and photocopy the list or digitize it so that you don't have to take the book to the field. Anyway, this is a very good book, full of very interesting objects. The Deep Sky Forum. The Deep Sky Forum is an amazing resource for visual deep sky observers. It has people from all over the world. I've seen Adarsha post on it. You hear from Jimmy Lowry, Dragon Nikin, Uwe Glan. These are all people who are very serious observers, and they all post here. It's a great place to discuss just deep sky objects. Cloudy nights is good, but this is specifically like cloudy nights for deep sky objects. So it's very good resource for visual deep sky observers. You can look for objects there. There are very cool objects listed. Every week they post something called the Object of the Week, and they do so much of background research on the object and share some information and share pictures. And once somebody posts it, everyone will share their sketches and their observing reports. So that's a very good resource. Okay. So here are some ideas for, some of these are beginner programs, but most of these are advanced programs. I'm just throwing out ideas for what are interesting programs. Okay, so you could say, I'll observe all 15 Palomar globular clusters. These are very faint, low surface brightness globular clusters. Or you say, I'm going to observe large planetary nebulae. So you can make your own lists like this. Anyway, I don't want to spend time going through all of this. I just cooked up a list to show like what's beyond the standard catalogs.
Akarsh, the catalogs that you're showing now, so do they also have the southern objects?
That's a good question. So obviously there is a large bias towards northern hemisphere simply because most of the world lives in the northern hemisphere, or most of the developed world, if I may say so, lives in the northern hemisphere. But Caldwell has southern objects. Many of these lists will not have southern objects, but I presume if you look for specifically for southern objects, you will find them. I presume that astronomy clubs in Australia have their own list. I remember hearing about some of these, and some of them contain objects from both hemispheres. But yeah, they tend to be overtly biased towards northern hemisphere, unfortunately.
Okay.
But if you
so
want,
the Herschel 400 also is only for the northern hemisphere, is it? Or does it have some southern objects as well?
That's a good question. I think Herschel 400 might be dominantly northern hemisphere. But there are very bright NGC southern objects. I just don't know where to find them because I've never gone down south. So I don't know. I don't know where to find those lists.
Yeah, I mean, my question is only what we can see from Bangalore or Rameshwaram or someplace in South India, like the little Pleiades or Eta Carina and so on.
Right, Eta Carina, Tarantula Nebula. That's true. I think for that I haven't gone beyond Cambridge Star at last because that's what I had when I was in Bangalore. Right. The other place to look for is German amateurs. They go down south. They have a observing site in Namibia, I think, and they keep going down there every 2 years or every year. And so they have actually lists of southern objects. So I'm not very familiar with it, but that's a good place to look for.
And do they also post in this Deep Sky forum?
Yeah, they also post in the Deep Sky forum. Deep Sky forum is very international. You'll see people from Cyprus, from Germany, from I don't know about Russia, maybe language barrier, but you see people from all parts of Europe, around the world.
Okay, thanks.
So another problem when you go to very faint objects is you seldom find them listed in your planetarium, right? Let's say you're using some sky chart or some astronomy software like Stellarium. If you look for like R237, it might not have it, right? So how do you find out where it is? So once you find out where it is and your planetarium software can plot it, then there is no problem because you can star hop to it. So for that, I recommend using these professional databases. These are made by professional astronomers. So for example, you can type pretty much, if you say by identifier here, you can pretty much type any object here. And this ICRS, this is its RA index. Okay, so you can you can find its RA index for almost any object. This is a professional astronomers database. So sometimes there are quirks. So if you say Able 39, for example, it will give you the cluster of galaxies. So if you want a planetary nebula, you should say some complicated thing, PN A6639, and then it will find a planetary nebula for you. But you can pretty much find any object in this. So that's how you go from the name of an object to its coordinates. You can just plug it into SIMBAD and NED. NED is the other one. NED stands for NASA Extragalactic Database. NED is very good for extragalactic objects. So it is not so good for globular clusters, nebulae, and so on. But if you want some faint galaxy, NED will have a lot of information on it. I hope this works.
Are there any mobile apps which can directly query from these databases?
I don't think so. I know actually K-Stars on the mobile does it, but you can just go to the website on the mobile phone.
Okay.
Here's an advertisement for K-Stars. K-Stars does this automatically. It might crash after it does it, but it does it. So it goes and queries SIMBAD and finds the object and puts it on your planetarium after that. So, but otherwise you can always copy paste the RA deck into your software after that, after going and looking it up on SIMBAD and NED. So whenever you see some obscure object, don't be afraid of it. Just put it in SIMBAD and you'll get the coordinates. Okay. Here's I already showed it to you on the web, so I don't need to show you this slide. This is just an example of what we just saw. Then let's talk about determining an observability, because I said when you choose a target, you want to make sure that it's well placed, it's feasible, and it's of interest to you. So I've already explained where to scout interesting objects, but how do you know whether it's visible or not? We have already gone over all of this magnitude, surface brightness, and said, okay, they're not very good, but they're okay. You can kind of use them. But what is much more powerful than these quantitative methods, which are like numbers, is the qualitative methods. By that, I mean verbal descriptions. For every NGC object, I think, for every NGC object, there is a description written by the compiler, JLE Dreyer, in a shorthand notation. It might say VB, which means very bright, and VL, very large, so on and so forth. So there's a shorthand description, and that's very useful to know whether this object is bright or faint. So for example, some of the objects say EEF, extremely, extremely faint. So you know that, okay, you're in for a tough challenge. But remember, most of the NGC was done with an 18-inch telescope. So chances are, if you have good sky conditions, you can see it in an 18-inch telescope. Other big resources are, so unfortunately, there was this website called ngcicproject.org, but the person who curated the website passed away, and the domain deleted it without a backup. So A bunch of people have been trying to put that website together back, and there's a partial reconstruction available. But to me, the most valuable thing on that website was Steve Gottlieb's notes. So Steve Gottlieb is a very good visual observer. He's an amateur like us, it's not his job to observe, but he's a very, very serious deep sky observer. He is the first person to visually see all of the NGC, all of the 7,800 or whatever number of objects are there in the NGC. And he has written very systematically notes on his observations of all of them. And many of his observations were done with 13-inch and 18-inch apertures. And so he has his notes available on the web. I've linked to it in the presentation. That's another very useful resource. So reports of other visual observers are very helpful. If they say it looked bright in a 20-inch, you might be not so afraid to try it in a 14-inch, right? So you can guess for your aperture. And like I said earlier, the unprocessed, roughly calibrated images like digitized sky survey, and these are two other sky surveys. PanSTARRS is very new. SDSS is the Sloan Digital Sky Survey. It's only the Northern Hemisphere. But DSS has both North and South. And DSS images are very useful for this. Because once you start observing, if you're using these DSS images as reference, then you will soon develop a sense of how the brightness in the DSS maps to the brightness in your telescope. So you'll be able to guess from the DSS image saying how difficult or how easy this observation will be, right? So if it looks extremely faint on the DSS, like averted vision on the DSS, then I would be afraid, unless it's a nebula. We'll come to that. So the qualitative methods are much more useful because I already told you what are all the problems with magnitudes and surface brightness. So this is how we determine whether something is observable. But ultimately, this is the motto of the Deep Sky Forum. Give it a go and let us know, right? Ultimately, it depends on so many factors. The only way to know whether something is visible or not is to try, right? Just try it and see if you can see it or not. So that's a long story on determining observability. I think my next slide tells you how to find DSS objects. There's a website. So there is this web interface. You go here and you first resolve the object. You say NGC 891. It's getting the array deck from SIMBAD. So that's what resolving means. It turned the name into an array deck. It filled in the array and deck for you. And then you choose the plate. Usually I prefer blue plate because red is the eye is not sensitive to red in the dark. So blue plates are generally better. And you want it in maybe GIF format instead of FITS. And you can retrieve an image and it'll show you an image of that guy. It'll get the plate, the digitized plate. I'm sorry I'm going through this very fast, but this is something that you can do at home, try, and this is how we all get these roughly calibrated images. Then there's the Sloan Digital Sky Survey, which is mostly Northern Hemisphere. It doesn't have very good coverage. The telescope is in the Southern United States. But it has other advantages. It's a much better image and so on and so forth. But like I said, most visual observers have a sense of the brightness of the object in their telescope by looking at the DSS plate. That's how we determine observability. Okay. I want to just say that I made a version of the DSS query that is much more amateur friendly. So this is hosted on bas.org.in. You just type in the name of the object. It does two things for you at once. It goes and queries SIMBAD, and it goes and queries DSS and gets the image for you. And the good part is you can rotate it, let's say, like that. And you can place a crosshair and it gives you the array deck and so on and so forth. You can adjust the zoom levels. So I created this because it was useful for me. So you can also use it. I'm trying to develop a version of this that can be downloaded onto your computer and used rather than going to the BAS website. But yeah, that's still in the works. So at this point, again, I'll pause and ask if there are any questions.
I have a question, and this is Jagan.
Yes.
So I might be an odd man here, but generally, when we go out in the field, right, to locate objects, I think the primary thing will be identifying the constellation and probably a bright star
Correct.
or a star which you can then move it. But generally,
Yes.
I do not have a sense of RA and deck. So how important it is to get that? Because you're saying many of these objects, right, immediately you get the RA and deck, right? So, but
Correct.
the sense of feeling is not there. So is it something very important to develop?
No, that's a very good question. RA index. I don't think. I mean, some visual observers have a sense of RA index. I don't know. I don't have a sense of RA index. Deck is easy because 90 degrees deck means it's very north. 90 degrees deck means minus 90 degrees deck means it's very south. It's at the south pole. So developing a sense for declination is helpful because it tells you if you're in the northern hemisphere, if the declination is like minus 70, then it won't rise very high. So declination might be useful, but RA, nobody has a sense for it. The reason I emphasize RA and deck is because it's a way of telling your software where the object is. So almost any software, if you enter you'll be able to enter the RA deck coordinates and ask it to center the thing, even if it doesn't know what the object is. So for example, your software like Stellarium or K-Stars might not have, or Sky Safari might not have anything beyond NGC. So if you want like, let's say, what's a good example? Colander 39 or something, which is an open cluster. It's a bright object, but your catalog, your software might not have it. So the best way to tell your software where to look, where this object is by finding its RA index and entering it into your software. That way, your software will be able to calculate where it is, show you the position relative to all the constellations, so that you can star hop to it. That's why I'm emphasizing RA index. It's just a way to get the object into your software if it doesn't exist.
Okay.
So developing a sense for it is not very essential.
Okay. Yeah. Got it.
Or even if you're using old-fashioned star atlas, let's say you don't take your computer to the field, which is fine. Uranometria will have all these lines, right? RA lines and deck lines. So you can mark on it on your star chart where the object is. Just put a pencil mark of the rough position and you'll be able to find it. That's why I emphasize RA deck.
Yeah, actually that's what I do. Normally I take either the Sky and Telescope Jumbo Atlas or the Sky 2000 Atlas, right? So with that, and normally that's how I do it.
Yeah, once you get to the point where you're looking for objects that are not listed in your atlas, this is the way to do it. Like look up the RA index and mark it on your atlas. There is a subtlety that I don't want to go into, which is RA index coordinates are referenced to a certain year. You will see, epoch, exactly. You'll see this thing called J2000 or ICRS. Just know that the standard of late is J2000 or ICRS. So you should use the J2000 or ICRS coordinates for any modern software or modern atlas.
Yeah. Okay. Thanks, Akash.
Okay. So, quick time check. I think again I'm running much slower than planned. So is it okay if I take like 15-20 minutes more?
I'm fine.
Okay.
That's fine, Akarsh.
Okay. So I'll try to get to star hopping today. So that's my plan. So these are anyway very light topics, so it should go through fast. So making a plan, is very essential before you go to the field, because night sky time is precious, and if you don't have a plan, it's very easy to lose motivation at 2 in the morning. When sleep is getting to you, you're looking at the sky saying, what shall I observe? And then you fall asleep. So a plan mitigates that and make sure that you have a goal always to. So I always recommend making a plan before leaving. It's yeah, it's easy to forget which objects you wanted to observe. When you were excited about them, you were looking at their pictures at your home. And then on the field, you won't remember which objects you wanted to see. So it's worth making a note of them and having a plan. And in the US, you cannot rely on internet access. In India, I'm told it's much better. But so it's worth having a list of what you want to do. And also what's worth having is a backup plan of brighter objects in case your sky condition is not as good as you wanted it to be. So if you only have a list of low surface brightness objects and then you go and the sky transparency is not good, then what will you do? You should have a backup of brighter objects. So how do you make a plan? You could just have a list of objects, but the important thing is you want to order them by RA, by Right Ascension. And the reason is the RA tells you which objects rise and set, right? The earlier RAs, the sky goes from earlier RAs to later RAs, if I remember right. So you want to order it by RAs so that you have a rough sense of order. You're not running around pages of your list. Or you can also group it by constellation, which I think is much easier. You just say these are the objects in Andromeda, these are the objects in Eridanus, and these are the objects in Fornax or whatever. And then you have a rough sense of, you look at the sky and say, okay, Fornax is high up. I'm going to try the objects in Fornax right now. Otherwise, you don't know where the objects are. So it's very hard to, you have to have some sort of ordering in your object. Okay. So I made long ago these log books I wrote a program to generate them, and they have a list by constellation, which you can use. The problem with the logbooks is I don't think their star charts are of very good quality, but you can use the rest of the stuff in them. Like they have DSS images and so on. An ideal plan will, I spent a lot of time trying to think about how to make the perfect plan, right? You want to observe the objects as close as possible to their highest when they are highest, right? Because then you're looking through the less of the atmosphere, and you allot sufficient time. So I kind of started out trying to make a plan that looked like a regimen, saying at this time observe this object for these many minutes. And my general feel is that never works. But an ideal plan will help you observe objects when they are as close to the meridian transit, that is the highest point, as possible. They allot sufficient time for objects. You have detailed finder charts and reference images. You have notes about what specific features you wanted to look for. Like maybe you wanted to look for a knot in M33. So you want to write that down somewhere. And maybe you want to also have other observers logs. But like I said, this is very detailed. It takes a lot of effort to create this. But this will give you much more mileage because you're always equipped with all the information you need. So there are lots of planning tools. There is something called Astro Planner. There is something called Sky Tools 3. These are paid software, which I've never tried. The free software, K-Stars, I contribute to this software. So I try to develop the observing list feature in the software to match whatever I think is as close to ideal as possible. That's a free software. There's another free software called Observation Manager, which I have not used a lot. But you don't have to use software. You could always use pen and paper. Various very good observers. Jimmy Lowry uses pen and paper. He just writes down a list of objects by constellation, like we have discussed. Steve Gottlieb and Alvin Huey usually use pre-made charts and books. That's also another way to go. Alvin Huey has very good observing guides on his website, which are, and he has all the right information he needs to star hop to the object in like less than 5 minutes is what I'm told. So different people have different ways of planning. You can try. I use software. Other people just use pen and paper, printed charts, whatever. But planning is essential. So this is what the observation planner in K-stars looks like. This is what I use. What I do is I sort it by current altitude, and I just pick the objects that are high right now. So it keeps recalculating what are the objects at the highest location. So that's very easy for me. Okay, so finally, before you leave for observing, you obviously have a plan with a list of objects. You know which good site you are going to, and you know that the targets are roughly within the range of what you can observe when you go onto the field. But there are a few more things that are very important. And probably the most important is that you want to be comfortable. See, there's no point in driving all the way, lugging your telescope, setting it up if you can't stay out at least till like 2 in the morning, right? Otherwise, it's kind of wasted time and wasted effort. So whatever is necessary to stay up, keep you alert and awake and refreshed all night is very important. It's as important as having good equipment. I cannot overstate the importance of warm wear. Sanat, who is a friend of mine also in BAS, he wanted me to make an entire slide on warm wear, and it's coming next. So warm wear is very important, and I'll explain why. It gets very cold when you're out in the open all night. You also want food. You want to have enough food and water, because the carbohydrates keep the brain and body powered at 2 in the morning. It makes a huge difference. If you're tired, you won't be doing good observation. And there should be water in your body. Otherwise, again, you won't be doing very good observations. The quality, it's not just the eyes that matter, it's the eyes plus brain, right? Like you want to be in the best of your capacities all night if you're doing observing. So these things are important. Visual observers should avoid alcohol and tobacco and so on, because it impairs night vision. And you want to have ladder and stool to prevent wringing of the neck, and so you're comfortable all night observing. Avoid equatorial telescopes for the same reason. Alt azimuth telescopes are much easier on your neck and body. And you want a place to sleep in the morning, especially if you're running multiple nights. Otherwise, at least so that you can drive back, or if you're not driving, then you can sleep in the bus, which is nice. But in the US, we don't have such luxuries. So here's the entire slide on battling cold. I was reading Galaxies and How to Observe Them. Like I said, that book has everything. And I found this line there: who only invests in the instrument but not in the right clothing cannot observe successfully. So when you're out in the open, it will be much colder for the following 4 reasons. One is rural areas are much colder than urban areas because people cause heating, like in urban areas. So this is part number 1. Your chances are you're going to go to a rural area, it's going to be colder. Second, there will be no obstruction for wind, so there might be more wind where you are observing, because your chances are you're observing in an open space. So there will be wind chill. Wind will blow away your body heat and make it feel colder than it actually is. Third thing, when you're out in the open, there is nothing to reflect heat back to you. So the heat that your body is generating is radiating into space. The air is a very poor conductor of heat, right? So air itself will not radiate heat very efficiently back to you. In an urban setting, you feel warmer because trees and buildings and so on, they radiate heat back to you. This doesn't happen in the open. So someone likened it to like cooling down to 3 Kelvin black body radiation. So you imagine the temperature is 3 Kelvins when you go observing. And then there is wetness that is caused by dew. So of course, we should avoid astronomy when dewing if possible, because it means that the humidity is very high. But that is impossible to do in South India, as we know. So we should account for the fact that dew causes wetness and makes things much colder. So for all these reasons, if you think you need some amount of warm clothing, you actually need much more than that. So here are some recommendations. this is from the books, Galaxies and How to Observe Them. You want to have an inner moisture absorbing. God, I wrote observing. It should be absorbing. So it's a moisture absorbing layer. You want a middle warmth retaining layer and an outer wind shell. And the outer layer, very important that it should be made out of acrylic or something that's not cotton or wool, because it can get wet because of dew. So that's important to think about. And heat loss primarily happens through torso and head. And so covering the head is very important. And for visual astronomy, you don't want to use gloves. If you can avoid gloves, it's best, because you're always changing eyepieces and adjusting your telescope and so on. So you want that dexterity. So I've sometimes used gloves and accidentally dropped eyepieces that cost a lot of money. So gloves are best avoided. Usually, if your hands are cold, it means that your chest is actually cold. Because what happens is when you're cold, the body changes the circulation pattern of blood so that it heats up the chest at the cost of your hands. So your hands and feet start getting cold if you are hypothermic, right? So if you put more layers on your chest, once your chest is warm, the body recirculates the blood so that the hands are warmer. So generally, cold extremities indicate a cold core, like your chest is colder. So you should put more layers on your chest. If you can avoid gloves, it's best. Sometimes you cannot avoid gloves, then I guess you just suffer. So that's the entire slide on battling cold. It's extremely important, because if you don't know how to battle cold, you cannot survive a night of astronomy. Here are some other tips. Always carry extra batteries of all types, AA, AAA, 9 volts, whatever. Carry a toolbox that are available to make small repairs in case you find that something is not okay with your telescope. I carry spare Teflon pads and glue in my telescope kit. That's how much particular I am. You obviously don't have to be that particular, but you should have something to at least jugaad your way into making your telescope work in case something is not working. And another tip is set up before sunset and use a portable fan if possible to cool the mirror so that tube currents don't cause problems. So that's everything about how to plan an observing session and what to carry before you leave and how to keep a plan and so on and so forth. I'll again pause if there are any questions at this point.
No questions, but I also wanted to just emphasize on this warmware. So even in South India, where it is kind of hot, we do get low temperatures. So when we went to Koratigere a few years back, it had gone to 9 degrees Celsius. So it was very cold, and we had to actually switch on the heater of the car and stay in the car. Fortunately, it was Navin Anjantappa's car, so it was okay. So yeah, so it's very important to have warm clothing.
Yeah. There have been many nights where we have shivered and suffered in Hosahalli. I remember this. I mean, even here of course, the best time to observe is when it is the coldest because the moisture is low in the air. So sometimes we have gone observing in sub-freezing conditions. The skies are amazing, but if we don't survive, what is the point? So hopefully Sanat will have time to talk about his Ladakh experience Leh experience at some point. But battling cold is an essential part of astronomy. So,
that's true. So I mean, when we went to Ladakh with Dr. Suresh Mohan, it was the same case. Like the temperature in the morning at morning 5 o'clock would be around minus 15 degrees Celsius. So it was really cold. I mean, basically changing the changing the lens at that time, and also pressing the camera buttons without the gloves was really painful. And because you had to use the gloves, press the buttons, and again put on the gloves.
Put on the gloves, yes, correct.
So ma'am also made a point on the chat that in South India and in hilly regions, you have to be also careful about wildlife.
Yes,
So
correct. Yes,
even
absolutely. Wildlife is a problem.
yeah. Even in Koratgere, we have sometimes, I think even Shubhankar has heard the sounds of bears. So
Yes.
it's not really. So yeah,
And
we have
there's also snakes that you have to be careful about, right? No, you should avoid cobras and things like that. It's very scary.
I don't know. I don't know. Maybe in the night they don't really come out because of
Okay.
cold temperature. But yeah.
Yeah.
Same with the snakes in the US. They don't come out at night, so it's relatively okay.
But there is a phobia, right? So in the night,
Yeah.
right? That there is always something there in the bush.
Yes, absolutely.
So that
Fear of
sometimes.
by Iron Maiden.
Sorry. So
Okay,
it's like
quick time check. I know it's been 1.5 hours since we officially started. Do I have enough time to cover star hopping, or should I reserve it for the next session?
I think it is better to start with in the next session with this one.
Okay.
Yeah, I think I agree because it's an interesting topic, and I think it will require good attention again.
Okay, cool. So then we'll stop here, and I just want to open for discussion. If anyone has any more questions, the talk is officially over. We can discuss if there are any questions, and then call it a night or call it a day.
So there was one
question. I have one question.
Yeah.
Yeah, please go ahead. Go ahead. Whoever is speaking.
Okay, so once I was trying to see the Virgo cluster of galaxies between Leo and Virgo, and I was told that if you just point to a telescope, you will see all the galaxies. But when I tried, actually, I did not see many. I could not see much, actually. Now, I just wanted to see if anybody had a similar experience, or even the Macquarien chain or the Virgo cluster also is difficult to see. It's not like you just point and you start seeing. That is what I wanted to check. Also,
see, it depends on your conditions and the telescope and so on. Okay, sorry, go ahead with your question.
Yeah, the other thing was sometimes you also may have these movements in the eye, right? Whatever, there are sometimes movements in the eye which is inherent to all of us. How do we differentiate between that versus, because I just got a feeling that, if there are very faint galaxies, you may be able to see it or you may miss it. I guess my question is, how do you identify objects in those kind of conditions?
Yeah, both are very, very good questions. And I will talk about the second question in the next session. But let me answer the first question. So the first question, it depends on what equipment you are using, what your sky condition was. So can you tell me what equipment you were using, what eyepiece you were using, what magnification you were at, and what sky condition you had?
So I was using 8-inch. I have a Skywatcher, Dobsonian, without tracking. And I tried 25 mm eyepiece, and then I switched to 10 mm. I do have the 2.5. I did not use that. So it was more so between 10 mm and 25 mm eyepiece that I was looking at. Sky conditions, I don't know on a broader scale what it would have been, but it was not very, very great. Yeah, so but it was okay. It was good enough.
Magnitude was. Were you able to see any, would you think we would be able to see Andromeda galaxy naked eye in that sky?
Naked eye, I don't know if that night, if I tried specifically, because it's a long time back, I don't remember. But it was not that dark. I don't think you could have seen naked eye Andromeda. And just to check, even naked eye Andromeda, you can see only averted vision, right? Not direct.
No, you can sometimes see direct vision. It depends on the sky quality and adaptation, dark adaptation in your eyes. But you can see, but usually it is averted vision. You're right.
Right. So I don't think on that night I could have seen it directly. It was not that dark.
Okay. Then I will say a few things. One is with a 25 millimeter eyepiece on an 8-inch telescope, you might get a field of view. I assume this is a Plausill eyepiece, like a Celestron Plausill or something like that.
Plausill, yeah.
So you might get a field of view of 1 or 2 degrees, not more than that. So your pointing accuracy in an 8-inch, if you just point anywhere in the Virgo cluster, chances are you won't see many galaxies. In an 18-inch, I will agree, like in a big telescope, 16 to 18 inch in a dark sky, you point almost anywhere in Virgo, there'll be a galaxy in your field. But in an 8-inch, you'll have to point more correctly at the Markarian chain. So the first thing is your field of view is pretty large. It's like 1 or 2 degrees, but it's not 5 degrees. So you'll still have to do some fine, at least some approximate fine pointing, which we will talk about in the next session. That's first thing. Second thing is, given what you tell me about the sky conditions, you might have had to stay there and spend about a minute or two at the eyepiece. Maybe not a minute, maybe 30, 40 seconds at the eyepiece with averted vision to see if there was anything in your field. But chances are, if you pointed in the correct location and you spent some amount of time at the eyepiece, then chances are you would see the entire Markarian chain. Maybe save for the last few galaxies in an 8-inch.
Right. So basically, it's all about having a higher field of view. Start with that and then identify the galaxies and then zoom in.
Yes,
so
absolutely. When I say the magnification, the ideal magnification for an 8-inch is going to be 80x, you don't start with that. You start with a much lower power eyepiece and to find the general location, and then you zoom in, like you just described. So
and that's the general approach I also take. But it's just that somebody told me that you just point and you will see any direction. So that is what I wanted to validate. Looks like that is not the case.
Oh, no. I think in an 8-inch, that is not entirely true. If you just point somewhere in Virgo, you will see galaxies. In an 18-inch, 20-inch, I agree. If in a sufficiently dark place, you will always have a galaxy in the field of view. But in an 8-inch, you might stumble on a galaxy, right? But it might take some effort to get the positioning right, because you won't be easily able to see, unless the sky condition is great, you won't be able to see those fainter NGC galaxies very easily at low power. You might be able to see them at high power again, but at the low finder eyepiece power, you might not see the fainter NGC galaxies easily. But at the flip side is, if you put the higher power eyepiece, then you have a smaller field of view. So chances that a galaxy is in your field of view are lower. So in an 8-inch, I won't expect that to happen. But in an 18-inch, yes.
Yeah, got it. Yeah, thanks.
Sure.
I have an observation or a question.
Yes.
So even for with respect to planning, right? So normally, earlier I used to go with K-stars. Then for some reason, I moved to the Astro Planner. But whatever it is, so before, I'm going to watch on a Saturday night, and this is my telescope or this is my binocular. And so I get a list of objects, and I kind of, what I do is segregate or list them per a constellation. But what happens is, like when we go into the field, because of the fickleness of the weather, right? So nothing works. So finally, when you want to watch something, whether the sky is not clear or something, and finally it is turning out that I end up having 1 or 2 constellations, and then I'll have to go back to my atlas. Then what are all the objects I've not seen, and then start covering them. So this planning is going haywire. So I don't know whether I'm doing some mistake or is generally what people are saying.
I mean, if the sky conditions are always a gamble, right? You might make all these grand plans and then go and see that the sky is almost cloudy except 2 constellations in the south. Yeah, what do you do? So I mean, if you have not finished all the objects listed in your sky atlas and they still interest you, then you always have the sky atlas. You don't need to make a plan because the sky atlas is your plan. So we observed like that for many years. But now I don't want to see any galaxy. I want to see an interesting galaxy. So it's come down to that. And that's when planning becomes important. But if you've still not finished all the objects in your sky atlas, and that itself can be a plan, you don't need to make a very sophisticated plan if you keep your atlas. And then you can do exactly what you described. You don't need to make a very sophisticated plan.
Okay. So
right? If you have an entire night clear, then all of this planning makes sense. You observe objects at the transit, but if the sky doesn't cooperate, nothing you can do.
Yeah, so I'm getting disappointed every time. Then I only wanted it to be productive as much as possible. So I thought having a good plan, would allow me to, space it out properly and, see as many objects as possible. But every time it's a disappointment.
So I recommend making that plan if you're sure that if you have a good chance that the entire night is going to be clear. Like this happens if you are observing in winter in South India and you don't have fog. Fog is a horrible thing. Now, if you don't get fog, and some night the fog is very hard to predict, but if you're high enough or whatever, you're not in a valley, you don't get fog, then if you're assured one clear night, then I think planning makes a huge difference because of exactly what you said. It optimizes how much you can see in that one night. But if you're not assured of a night, then it becomes very hard. Like you don't know what the weather is going to do. It's a very disappointing hobby. Really, chances are, weather is such a fickle thing. So many nights we would have gone with very high expectations, and nothing will happen because fog comes in or whatever. This is the life of this hobby, right? There is nothing we can do to account for that. The way we worked around this when we were young is Amar and I would if we see one patch of blue in a sea of cloudy skies, if we see one patch of blue, we will go observing that night and just try our luck. This is how we used to observe. We would just keep trying our luck, and sometimes we got lucky, sometimes we didn't.
Yeah, that happens. Okay, thank you.
Yeah, there was a time when every new moon weekend, irrespective of the weather prediction, we would go.
Yeah, I think this is where the company matters a lot. So if you have a good company, whether you have the sky or not, you would just go and just try to enjoy how much ever is possible.
I agree with that, Kirti. That's very true. Any other questions, discussion?
Yeah, I have a question. But it relates more to equipment than observing.
Okay, sure.
Supposing I want to get a bigger telescope for deep sky observing, and I have used an aperture like an 8-inch or a 10-inch. And is it worth buying something with a larger focal ratio? Not extremely large, but something more than an f5, something like f6 or f7, because that is claimed to be where the optical stability is at the highest. You don't have optical issues.
That is true.
Yeah.
Yeah, what you're, I think, saying is that f3 mirrors, focal ratio 3 mirrors are much harder to make than focal ratio 6 or 8 mirrors. That is very true. But on the flip side, if you buy a large aperture f8, like a 10-inch f8 or a 12-inch f8, it's going to be very hard to transport. So it's a compromise. Most of the big telescopes that people observe with, the really big Dobsonians, are f4 to f5, simply because of the transport.
Okay.
F3, people don't avoid going down to f3 because of this optics issue, but I've seen very good scopes that are f3. It depends on the quality of the optician and what the chance of getting a good mirror is. Yeah.
Okay.
If you know something is a good mirror, it doesn't matter. You can buy f3. But if you don't know, you're buying in the dark, then yeah, it can be a problem.
Okay.
Actually, I forgot to answer the second question in the previous that was asked previously. I said I'll answer it in the next talk, which is how do you see that? How do you know that you are actually seeing? I think the short answer is experience. You learn to trust what you can see and cannot see from experience. And yes, there are floaters in your eyes during the day, especially. And I like to say that there is some noise in your eye at night. And I'll talk about this in the next talk. Yeah, but I think experience is the answer to that question.
Also, kind of comparing the observations of each other, like the orientation of the object.
Yes, absolutely.
But maybe you will cover these in the next session. So let's.
Yeah, I have some points, but we can, it's just one thing that I'm going to cover. But yeah, that's exactly right. The experience of where many observers will agree. That's how you know that it's. And as you get more and more used to this, you will know what is real and what is not at the threshold of observing, right? Yeah, I remember one crazy case where we were trying to see Horsehead Nebula from Coorg. This was in 2009. And I think it was Kirti's 8-inch. I'd seen it in the 17.5-inch, filter and all of that. Not too hard. I mean, very hard, but for our level of experience then, it was okay. And then I went to the 8-inch and I said, I can't see it. And then I said, wait, I see something that's there. Something black is there, but it's not in the same direction. And then I realized that the 8-inch was mounted on equatorial mount. So the orientation was actually different in the 8-inch from the 17.5-inch. That's how I know that I've seen it. Because it was because I saw it in an unexpected orientation. And then I realized that it made sense. So yeah, even though I was looking for it in a certain orientation, that was not the orientation in which I saw it. So that's how I know it was an observation. That's just an example.
Yeah, I still remember that. Yeah. So yeah, it was indeed my 8-inch telescope. There is one more question, which is there something like a fisheye eyepiece for telescopes which can give very wide field of view for identifying the object?
I see. So I've never heard of fisheye eyepieces, but I think you're talking about like the wide field eyepieces like Ethos and Delos, or what is it called? Ultra wide angle from Mead, Explore Scientific 92 degrees, all of these things, right?
Yeah. I think so. Yeah. So I think Ethos is the largest, probably.
It's a 100-degree field of view. Ethos is a good eyepiece, but for the rest of it, I would actually prefer a well-coated orthoscopic. We'll get into this. I think the right thing to optimize for is contrast and not field of view, because unless you're going for very diffuse nebulae, low surface brightness things, then field of view might matter. But for most objects, you want to optimize contrast rather than the field of view. So I actually prefer Delos eyepieces. They are also expensive, but they're not as expensive as Ethos. And but if you don't want to spend that kind of money on eyepieces, good multi-coated orthoscopic eyepiece is really good. You don't need the field of view of an Ethos, or I would much rather spend my money on contrast than on field of view. And we'll get to it. Yeah, at some point I thought Nagler eyepieces were everything because they had this 82-degree apparent field of view. But now I try to stay away from the Naglers because they have more elements.
Okay, great. So that's wonderful. I didn't know that you have moved out of or moved away from the Nagler eyepieces now.
I still use them, but I try to use Delos a lot more.
Nice. So you are spending so instead of spending money on lenses like us, you are spending money on eyepieces.
Yes, absolutely. This is the funny thing about this hobby. I think my eyepiece kit and filter kit costs more than my telescope.
I think in any hobby, if you want to go to the next level, you have to spend that kind of money, right?
I want to say visual observing is a little more forgiving because you don't have to. The primary investment in visual observing is time and patience more than money. Equipment is equipment will help. If you want to go further and further, yes, there is no argument. But I think more than equipment, what matters is dealing with the frustrations of going to a site and staying up all night and then finding out that it is cloudy and all of that.
Yeah, that's true.
Yeah, but definitely my eyepiece kit is at the point where my accessories cost more than my telescope. So, but also my the telescope is second hand, so I got it at a very good price. So that should be factored in.
Awesome. So I think there are no more questions for today, at least in the chat. So if nothing else, then we can close the session for today and meet next week again.
Yes. I hope this was useful. We'll meet again next week, similar time.
Yes, very useful. Thank you for the session. I've learned a lot, and I will make use of all these things that you have said.
I'm glad to hear that. Thank you.
Yes. Yeah. Thanks a lot, Akarsh.
Thanks,
yeah,
Akarsh.
For me also, it was very
Thanks,
enjoyable. And nice.